Yeah, so the qualitative analysis report just lists the cations you've tested positive for and a list of the anions. So a very simple report. Okay, any other questions? I think we left off last time. Did we do the concentration cell? I think we did. And then the pH meter is one application of that. Although nobody would make a pH meter like this. Did we already talk about this? No. Okay. This is another example of a concentration cell where we have on one side we have platinum, on the other side we have platinum as well. So we put two standard hydrogen electrodes side by side. And if we have the same amount of H plus on both of these, then it would be a tie. So we're bubbling H2 gas here, and then we're bubbling H2 gas over here. And so we're looking at H plus over here and H plus over here. And the only way to make this work is, because we have the left side and the right side are identical, the only way to make it work is to change the concentration. And so we can make one side stronger by increasing the concentration, that is strength by numbers. And so over here, there's going to be no flow, because it's a tug of war, H plus versus H plus. But if we have more H pluses on this side, then the right side's going to win the tug of war. And so what we do is we make this side more concentrated, cathode side, and on the anode side, we make it less concentrated. And so the electrons are going to flow left to right. And the voltage is going to be determined by what the imbalance in concentration is. And so the higher the concentration difference, the higher the voltage. And so here, we'll have this, will be the reduction potential over here. So we'll have 2H plus, and this is going to be at the higher concentration, in this case 1 molar, plus 2 electrons goes to H2 gas. H2 gas is just going to be under standard conditions. It's 1 bar. Then over here, I'm going to have a lower concentration H plus. And so over here, I'm going to have H2 gas go to 2H plus. This is going to be an X molar plus 2 electrons. And so this is, when I look at the cell diagram here, what I have reactant to product. So this would be at the anode, reactant to product. So at the anode, I have reactant hydrogen to product H plus. And the H plus concentration is going to be X molar here. X has to be less than 1, otherwise electrons aren't going to flow. So X must be less than 1 molar. If X were equal to 1 molar, then it'd be a tie, 1 molar versus 1 molar. If X were greater than 1 molar, then electrons would flow backwards, because the left side would win because of the war for electrons. And then we have salt bridge, and then on the cathode, I have H plus. 1 molar goes to H2 gas. And so at the cathode, we have H plus of 1 molar goes to H2 gas. Yeah. And so this is going to be under non-standard conditions. And so E of the cell under non-standard conditions is equal to E of the cell under standard conditions. Minus 0.0592 volts over Z log of Q. So going back to this here, the standard cell potential is going to be 0 because here we have to have 1 molar and 1 molar. So if we have 1 molar versus 1 molar, it's a tie. Neither side wins, and there's going to be no flow of electrons. The number of electrons transferred, Z, is 2. And so this is going to equal minus 0.0592 volts over 2 log of Q. Q is going to be the product over the reactant in the net reaction. So let's take a look at the net reaction. The net reaction is going to be H2 gas plus 2H plus. So this will be 1 molar here. Is going to produce 2H plus at X molar plus H2 gas. And so Q for this is equal to the product. And so we're going to have H plus squared times the pressure of H2 gas here divided by the pressure of H2 gas here times H plus squared. Except this is going to be H plus at 1 molar squared. This is going to be H plus at X molar. We don't know what that is. And so basically this is going to be 1. This is going to be 1 bar, and this is 1 squared. And so the log of Q ends up just being the concentration H plus the X molar squared. Okay, then what we're going to do is we're going to do this out. It's going to equal 0.0592 volts over 2. I'm going to do this. I'm going to put this as negative log of the H plus squared. Then I'm going to bring the 2 in front here. So this will be just 0.0592 volts. And the negative log of pH of the H plus is just the pH. So the pH is equal to E of the cell divided by 0.0592 volts. So we just measure the cell potential and we can convert it to pH. And so this would be a pH meter in function. The 2 I brought to the front. And then I canceled it. Yeah. Property of logs. We do that. So nobody would ever build a pH meter like this because you have to be bubbling hydrogen gas. You'd be wasting a lot of hydrogen gas. But in theory, you could see it would work or function as a pH meter. In fact, all these pH meters rely on setting up a cell here. So these are the traditional glass electrodes. These bulbs here are sensitive to H plus hydronium. And you can measure the potential difference, that is the difference in concentration of the cations inside and outside. And that'll set the voltage. That voltage you can convert to pH. So these are traditional pH meters here, pH probes. There are others like that are rely on silicon chips that are a lot more robust. And so modern day pH meters would be something like this. Would have a ISFET probe. Should look like this. These are log. a lot less finicky than the normal pH probe. So you just have a little silicon chip there to measure pH. We only need a drop of solution. You can measure semi-solids, other things that you can't typically measure with a glass bulb. The glass bulb, there's a gel on the outside of the bulb, and if that gel dries up, then the response from the pH meter becomes extremely slow. So you've got to maintain, that gel has to stay hydrated. And this is why these glass bulb pH probes have to be submerged in solution all the time. So once they dry out, they take a long time to rehydrate. And you'll have a very slow response. Did I do this problem earlier? This is the KSP of PBI2. I'm a lot further.
We left off with the platinum and iron equation, for example. So.
Okay, this one here.
Iron and silver.
Yeah. Okay.
Yeah.
All right. Okay, this is the same kind of deal here. And so it's another concentration cell. At the anode, we're going to have lead and lead 2+. This is going to be saturated PBI2. Saturated PBI2 means the concentration of Pb2 plus is very low because PBI2 is insoluble. And then over here at the cathode, we're going to have lead, and then we're going to put Pb2 plus at 0.100 molar. And so as long as the concentration here at the anode, that is the Pb2 plus concentration at the anode, is less than the Pb2 plus concentration at the cathode, then the electrons are going to flow left to right. So this is just strength by numbers again. There are going to be more Pb2 pluses here, so the right side will win the tug of war for electrons over the left side. So this is another concentration cell, and we can use the Nernst equation for that. E of the cell is equal to E naught of the cell minus 0.0592 volts over Z log of Q. E naught of the cell is 0 volts because if this were, let's say, 1 molar and 1 molar under standard conditions, then it would be a tie. There would be no flow of electrons. So under standard conditions, the two lead ion concentrations are the same. We don't expect electrons to go left or right. Minus 0.0592 volts over Z. What is Z? Well, over at the anode, we expect this to happen. Pb solid is going to be oxidized. Oxidation occurs at the anode, so we're going to form Pb2 plus 2 electrons. Over at the cathode, reduction occurs, and so we expect to form Pb2 plus. Pb2 plus should gain 2 electrons to form Pb solid. Okay. And so this would be the reactant product at the anode. In the product here, this is going to be saturated PBI2 concentration. Over here, this would be reactant product at the cathode, and the reactant over here is going to be 0.100 molar. Okay. And so there are 2 electrons transferred in the balanced. So these 2 moles of electrons log of Q. Q is going to be product over reactant, so the overall reaction is going to be Pb solid goes to Pb2 plus, and this Pb2 plus is going to be saturated solution. And then we're going going to have Pb2 plus over here, Pb2 plus at 0.100 molar. And then this is going to go to Pb solid. Well, the activity of pure solid is 1. And so the log of the product will be the Pb2 plus at the anode, which is the saturated, divided by the Pb2 plus at the cathode. The Pb2 plus at the cathode is 0.100 molar. So this is 0.100 molar. So E of the cell here is 0.0567 volts. That's what we measure, 0.0567 volts. And so let's solve for the Pb2 plus concentration at the anode. We have 0.0567 times 2 divided by 0.0592. And then we'll take the anti-log of that. And then we'll multiply by 0.1. And so what we end up with here is a lead-2 concentration that's equal to 0.0012147 molar. Okay, that's a lead-2 concentration in saturated PbI2. So this is the anode, which is saturated PbI2. Okay, in this particular problem, what we can do is we can solve for the KSP of PbI2. PbI2 solid goes to Pb2 plus 2 iodide. So initial, let's say there's 0. And then the change is going to be plus S plus 2S. And so at equilibrium, I'm going to have S and then 2S. And so the KSP here is going to equal lead concentration, which is S, times the iodide concentration squared, which is going to be 2S upon the D squared. And so the KSP is equal to 4S cubed. Well, S is the same as the lead concentration here in the saturated solution. And so this is actually equal to S here. So we can plug that in here and solve for the KSP. And so I'm going to take the S and then cube that times 4. And I get a KSP equal to 7.1687 times 10 to the minus 9. And probably about 2 sig figs or so. So 7.2 times 10 to the minus 9. The actual KSP is a bit different, because there's ion pairing and other things that can happen. Plus the KSP calculations, by ignoring those types of species, like this one. This is one I wanted to do with visual Mintech, but I didn't have everybody do this one. But this is a good one to do with visual Mintech because there are a lot of ion paired species, which increases the solubility. Right now, the solubility just depends on this species, but there are multiple lead species that actually form, in solution, which means that solubility is quite a bit higher. Its actual solubility is quite a bit higher. But this is a way we can experimentally determine KSP. Okay, so those are examples of using the Nernst equation. Next, we're going to talk about batteries here. Batteries are an important application for these voltaic or galvanic cells. We have primary, secondary, reserve, flow, and fuel cells. Primary battery, all primary batteries is hard to recharge this battery. The reaction is irreversible. But once you're done with the primary battery, you just dispose of this. And so this is your standard battery here. The oxidizer is kind of strange because the oxidizer is solid manganese 4 oxide. Manganese 4 is a pretty good oxidizer, and it's inexpensive. The problem with manganese 4 oxide is it's a solid, and therefore you have to get it in contact with the cathode. The cathode is just graphite carbon solid. And the way you get the manganese 4 oxide or manganese dioxide crystals in electrical contact with the cathode is by using a graphite paste. So there's a graphite paste there. Graphite's a conductor of electricity. And so as long as the crystals of MnO2 are in contact with the graphite paste and the graphite paste is in contact with the graphite rod, then we have electrical contact. And the MnO2 will take some water from the paste and 2 electrons from the electrode, Mn2O3 and 2 hydroxide. Now the anode is just zinc metal. And zinc metal is coating the inside of the can. And zinc is an excellent oxide, excellent anode because of its high oxidation potential. It's easy to oxidize. So the cell potential for this is around 1.5 volts, except they do something very interesting for this. The cell potential would decrease rapidly as the zinc ion concentration increases and the hydroxide ion concentration increases. As these concentrations increase, the cell voltage decreases. But what they thought of is they thought of some interesting chemistry here, and that is the hydroxide they prevented from building up by adding ammonium to the electrolyte. If they add ammonium to the electrolyte, then the ammonium reacts with the hydroxide to form ammonia and water. Ammonia is gas, water is liquid. And so what happens here is that the concentration doesn't change. Or the activity, the activity stays equal. But they go beyond this. That is, ammonia gas, you don't want ammonia gas to build up in here because that would create pressure, gas pressure, and potentially it can lead to explosive, pressure explosion, explosive canister if it's heated in a fire or something like that. And so what they do with ammonia is they complex it with zinc to form the diamine zinc complex cation. Not only that, they'll precipitate out with chloride because it turns out that diamine zinc 2 chloride is insoluble. And so overall, what happens is this. Normally, Nernst's equation says the zinc ion concentration increases and voltage decreases, but that zinc is complex with ammonia and then precipitated, so we end up forming a solid. And then the hydroxide increases, the potential should decrease, but the hydroxide is eliminated by converting it to ammonia, and then ammonia ends up complexing. And so it's a very interesting reaction. The very interesting reaction is we go solid, zinc solid, and MnO2 solid. This is liquid, goes to solid, and then this would be a liquid, and then a solid. And so in this reaction, we're reacting solids and liquids and forming solids and liquids. And solids and liquids have an activity of 1. The activity doesn't change, the concentration doesn't change. And therefore the voltage stays stable. And so one of the tricks to getting stable voltage in a battery is by using as many solids and liquids as possible. And that's what's done here, because if the voltage starts dropping off immediately, then that becomes pretty useless quite quickly. If the voltage would drop off like this, according to the Nernst equation. And a lot of electronic devices require certain minimum voltage to operate. So, this is the irregular heavy-duty battery. In an alkaline battery, they put hydroxide in there. So the hydroxide in the electrolyte here will precipitate out zinc hydroxide, which is solid. So I think it's just a little bit more expensive than ammonium. So this is why alkaline batteries are really cost more. But the same concept. Try to form solids. Here's a car battery. Car battery actually consists of 6 batteries put together. Each battery generates at 2 volts. And if you have six of them in what we call series, then you generate 12 volts. Car batteries do 12 volts. The oxidizer is a solid again. The oxidizer is lead-4 oxide. So the lead-4 oxide, the crystals of that have to be contained in a conductor. A conductor can be lead and metal. Okay? And so we have lead-4 oxide as the cathode. And lead will be the anode, lead metal. But again, in this case, rather than forming ions, they're trying to form solids. If we form solids, then the voltage stays fairly stable. Although here we're forming some ion, H+. And we have to make sure that there's sulfuric acid present in this battery. So this is the overall reaction. The number of electrons transferred is kind of weird because here we're starting at lead 2+, and then we end up with lead 0. So that one of those leads gained 2 electrons. The other lead, we go from lead 2+ to lead 4, and so the other lead lost electrons. So lead 2 sulfate here is both the oxidizer and the reducer. One of the leads is reduced, the other lead is oxidized. This is a rechargeable battery, a secondary battery. And so you can reverse this reaction by hooking it up to some external power supply and then just forcing the electrons to go backwards in the cell. Some reactions are easier to reverse than others. This one is very difficult to reverse here. This is for the silver zinc button battery. The oxidizer again is solid, and so it's better to use solid oxidizer as possible than aqueous because then voltage remains more stable. The silver oxide, and that gets reduced to silver, and then we'll have hydroxide here. But the way that hydroxide gets gotten rid of is interesting here. The hydroxide can migrate over to the zinc, and we end up forming zinc oxide here, rather than just Zn2+. And so the overall reaction is solid, 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 solid. And so the voltage doesn't change much through the life of this battery because the concentrations aren't changing. Eventually it'll run out of reactants and then the voltage will drop off dramatically. Here's a rechargeable nickel cadmium. So this reaction is easy to reverse. And so you can recharge this one without too much difficulty. His lithium-ion battery. Lithium-ion batteries take advantage of these layered compounds. These layered compounds, what's holding these sheets together are just London dispersion forces. So what you can do is you can insert lithium ions in here and create a high potential. So you can charge it by forcing lithium ions between the sheets like a sandwich and then discharge it by letting in lithium ions. And so we have these layered compounds in lithium-ion batteries. This is called intercalation. This is a reserve battery. A reserve battery is, there's no electrolyte here. Electrolyte would be like the salt bridge. So what you do is, once you put electrolyte in there, it's like removing the salt bridge on ours, 1 down to 0 volts. The same thing here. And then you have to start the salt bridge, it's going to start working. So it's just a reserve shelf life. It's like a dried out battery. And once you hydrate it, then it'll start working. This is a fuel cell. Fuel cell is you just keep adding reducing agent. In this case, is hydrogen. Oxidizing agent is oxygen. So in a fuel cell, you can keep adding fuel, which is hydrogen. The oxygen comes from air. So here's the net reactions. Here's the reduction. Here's the oxidation. And overall, it's hydrogen plus oxygen plus water. The voltage is 1.229 volts. It's a pretty efficient way to generate electricity. So. This is another battery, aluminum air. So the fuel's kept in here, and then air is the oxidizer. So this would be the anode, and then the cathode would be whatever is interacting with the oxygen in air. Usually like graphite, carbon. Carbon's cheap. And we talk about corrosion. Corrosion is also a battery, but it's not used to generate electricity here. Corrosion, you think corrosion or rust is fairly straightforward. When you think about rust, it's just oxidation of iron. So it seems like a simple enough reaction. Iron and oxygen yields Fe2O3. But it turns out that corrosion is a little bit more complicated than this. Like, for example, if this were dry iron doesn't really corrode. If this were wet, then it corrodes slowly, wet with DI water. If this were wet with salt water, then it corrodes quite rapidly. And so why is that? Why is it? It's because this reaction is a bit more complicated. This reaction is actually a battery, an electrochemical cell. And so what we have here is we have iron. I go through this in Lucium as well. Iron's the anode, so we have an iron nail here. And to further study the process of corrosion, you take this iron nail and hammer the ends. When you hammer the ends of the iron nail, it introduces defects. When you put in defects, that makes those atoms even more susceptible to oxidation. So it's easier to oxidize these atoms in the end than these atoms here. So this is just one nail that's been hammered. And so what we have here is we're going to oxidize the iron atoms that are easiest to oxidize. And the iron atoms that are easiest to oxidize are here and here. And so when we oxidize those, we generate iron too. And then over here, the oxygen comes into attack. The oxygen comes into attack and take electrons. But when they take electrons, they're taking electrons from the end here. When the oxygens come in, and there's water present, we're going to form hydroxide. So they put a few drops of phenolphthalein in here, and we can see the hydroxide form here. And so this would be the cathode, where the oxygen comes in, forms hydroxide. And these will be the anode, where the iron 2 forms. And so once we form iron 2 and hydroxide, then it's going to stop. There's no salt bridge here. But there's no salt bridge, but the anions can migrate to the anode just by diffusion through the solution. And so the hydroxide is generated here, and it can migrate to the anode. The cations can migrate to the cathode, and that will neutralize the negative charge buildup at the cathode and the positive charge buildup at the anode. But what happens is hydroxide moves much faster than iron because of its mass. Hydroxide is a lot lighter. And so the hydroxide moves much quicker towards the iron. The iron 2, once it's generated, reacts with the hydroxide and forms a green precipitate. It's hard to see, but there's green precipitate here and green precipitate here. Showing that. Okay, this is another iron nail, but this iron nail's been hammered on the ends and bent. When you bend it, you create defects here, and those defects are going to make the iron more susceptible to oxidation, increase its oxidation potential. And so we have 3 anodes, here, here, and here, and 2 cathodes in this case. So cathode, oxygen is generating hydroxide. Anode will generate iron 2. And then the hydroxide goes towards the anode and precipitates out iron 2 hydroxide. So we get green precipitate here, here, and here. So this happens slowly in DI water. If I had salt water, it happens much more rapidly because as soon as I generate the hydroxide, it doesn't have to diffuse over here. As soon as I generate the hydroxide, it will be stabilized by cations in salt water. And as soon as I generate the iron 2, it will be stabilized by anions in salt water. And And so corrosion happens much faster in salt water because now we have a salt bridge rather than having to wait for the cations and anions to travel one another to the opposing electrodes. Also, an acid, and that has to deal with the reduction potential. If we look at the reduction potential of oxygen and water forms hydroxide, and that reduction potential is 0.4 volts. It's not very high compared to the reduction potential in acid. So if I look at oxygen plus 4H pluses, this yields water. Water is a much more stable product than hydroxide. So in this case, the voltage is going to show that 1.229 volts, which is much higher reduction potential. And so we'll generate a higher voltage here, 1.2, this will be more like 1.6 volts versus 0.8 volts here, if there's acid present. So we try to prevent corrosion. One of the ways of preventing corrosion is by galvanizing iron. So this is galvanized iron here. Galvanized iron is just putting it into electrical contact with zinc. Now, the oxidation potential of iron is less than the oxidation potential of zinc. And so what's easiest to oxidize? Whatever has the highest oxidation potential, in this case zinc. So if oxygen comes around to try to attack iron, it's not going to be able to pull it off the electrons here on the iron because zinc is an electrical contact. If zinc is an electrical contact, then zinc has a higher oxidation potential and it's going to be oxidized. So zinc gets oxidized to Cn2 plus. The oxygen comes oxygen is going to convert to hydroxide. Now, this is called a sacrificial anode because what we're doing is we're taking the normal anode, which would have been iron, here. You can see the corrosion of the iron here, here. And then using an alternate anode, which in this case is zinc. That's going to protect the underlying iron. So oxygen might try to attack the iron directly, but it's not going to be successful because it's going to just take from the zinc. Here's some galvanized nails here, some zinc-coated iron. Eventually, all the zinc is going to be oxidized, that is. It's all going to react. And then once that happens, then the underlying iron can be attacked. And the iron will start to corrode. And so these are going to have some finite lifetime. Pretty soon all the zinc is going to be gone, and then the iron is going to start to corrode. And when that happens, it's going to lose its structural properties. We usually use those as building materials. So what we can do is to prevent something like that happening, you can have replaceable. So we aren't going to recoat our nails. Once they're in the wall, you can't do anything. Just hopefully you have enough zinc to protect the iron for the life of the building. Here, we aren't going to have enough sacrificial anode to protect them both. And so they have replaceable units here. These are sacrificial anodes of magnesium. So magnesium versus steel, magnesium has a higher oxidation potential, therefore magnesium will be oxidized. Once that's completely oxidized, then you can replace the sacrificial anode, we call it, and generate more protection for the steel. You can buy sacrificial anodes at Home Depot for plumbing systems, that kind of stuff. There are other ways you can protect it. You don't have to galvanize it. You can use some magnesium sacrificial anode. You can put in inert coating so that both is painted. And so paint provides a barrier here, so oxygen can't come in and attack it. Non-conductive. Unless the paint has cracks in it. If the paint has cracks in it, then it'll start corroding with the cracks in the paint. We could also try putting copper coating. That's what's shown here. Copper coating would be an inert coating. This air would have a much more difficult time oxidizing with copper. Unless there are cracks in the coating. If there are cracks in the coating, then we're going to have corrosion just as we had before. And so here's copper graphed on the penny. You can see that iron is the anode, and the cathode is copper metal here. Okay, so this is some brief commentary on corrosion. Take a look at the zoom up. Okay, we talked about secondary batteries before, and how do you recharge a secondary battery? How do you recharge a secondary battery is with a power source there or an alternate battery here. And so we have a power source here. We hook up the positive to, positive would be the cathode. We hook it up to the anode of the cell. And what we want to do is we want the electrons to go from right to left. We want them to flow backwards. Okay. And so essentially what we're going to do is we're going to pull electrons here. That means whatever's in contact with this will become oxidized. So copper, in this case. Copper will be oxidized, will generate more copper too. And the electrons will come over here and they'll reduce something like zinc ions. Zinc ions will be reduced to form more zinc metal. And so here we're going to regenerate our copper 2 ions, and over here we're going to regenerate our zinc metal. And so that will be recharging this battery. Okay. We can also use electrolytic cells to generate high energy chemicals. What batteries do is batteries take chemical potential energy and convert it to electricity. In electrolytic cells, what we're going to do is we're going to take electrical energy and convert that into chemical potential energy. And so this is electrolysis of water over here. So we hook it up to an external power source, this battery, 9-volt battery. And at one of these, the electrons are being pulled into the battery. Which one is it? So if we look at this will be the cathode. Reduction occurs at the cathode. And so water takes 2 electrons to generate hydrogen, hydroxide. This would be the anode. Oxidation occurs at the anode. And so the anode, we have water gets oxidized to oxygen plus 4H plus 4 electrons. So which one is this? Well, we can tell based on the ratio. Usually convention is we'll go right to left electrolysis, but it really doesn't matter. But if we kept convention, we're going to take electrons from here and force it. So this would be the anode of the cell going to the cathode of the battery. We'll suck the electrons in. And we can tell that this one is indeed the anode of the cell because we're going to have oxidation occur here. When we oxidize water, which atom do we oxidize? When we look at water, there are 2 things that can happen with water and redox. If we look at the oxidation states, hydrogen is +1, oxygen is -2. And so we aren't going to oxidize hydrogen, it's already missing electron. We're going to oxidize oxygen, so we'll take 2 of these and we're going to form O2 gas. O2 gas is going to have oxidation state of 0. And so here we're taking the 2 electrons off each oxygen, so a total of 4 electrons. The hydrogen is not going to change, it's going to be 4H plus in terms of oxidation state, plus 4 electrons. And so this is what happens when we oxidize water. When we reduce water, this is the generic symbol for oxidation. Those square brackets with an H. O. When we reduce water, we use this. This is the generic symbol for reduction. We end up generating hydrogen gas. And in this case, we'll have 2 hydroxide. So when we oxidize water, we form oxygen gas. When we reduce water, we form hydrogen gas. So we're doing both here. So when we oxidize water, here we're going to form oxygen gas. And which one of these is oxygen gas? Well, you can tell based on the volumes here. We form hydrogen, twice as much hydrogen. Oxygen. So this hydrogen must be forming here. If hydrogen is forming here, then the electrons are being pushed in here in water. We're reducing water. That means electrons must be being pulled out here. So this is drawn differently than my convention. But it doesn't matter how you draw it. You should be able to figure it out. And so over here we have oxygen. Over here we have hydrogen. I can tell this is hydrogen because there's twice as much hydrogen as there is oxygen. And so what's happening over here, oxygen is being oxidized from oxygen gas. And being oxidized to it's being oxidized, this would be the anode. And so this is kind of drawn differently than the way I'd drawn it earlier. I like to put the anode on the left here and have the electrons go right to left, go backwards. In this case, I have oxidation occur at the anode here, so electrons are being forced through here and then traveling to the other side over here to produce hydrogen in water to form hydrogen gas here. So this is electrolysis of water. Now, one thing that I'm showing you this here, for a voltaic cell, one thing that we see is in voltaic cells, we generate electricity. So delta G is less than 0, it's spontaneous. In an electrolytic cell, we have to use electricity, and that's because the reactions are normally non-spontaneous. And we have to force the reaction to occur by using an external power source or power supply or battery. Now, there's something weird about the sign. So, for example, anode, what happens at the anode? Oxidation occurs at the anode, no matter what. If oxidation occurs at the anode, then we generate electrons at the anode. So normally anodes are given negative sign, so anodes are negative. But over here, this is weird because here we're generating electrons, but they're calling it positive. And so there's something screwed up with the signs of electrolytic cell. And what's screwed up about it is this. Here. If this is the positive of our battery, then this should be the negative of our cell, because here we're generating electrons. We're generating electrons through the oxidation to copper 2. We generate electrons flow in the circuit. So when we generate the electrons, that's negative. And then over here, this is negative of the battery is forcing electrons. This is where we're consuming electrons, so this should be positive. But what a lot of people do is they ignore the sign on the electrolytic cell and just look at the sign on the battery. And so this is why they call the anode positive, because it's attached to the positive terminal of the battery. But normally we would think of the anode as negative because that's where we're generating electrons. And so this sign convention, a lot of people just ignore it. You know, it's confusing, and they should just be consistent. It's okay. Here's some other applications of electrolytic cells. Copper refining, coating stuff, like electroplating, was coating like chrome on steel, chrome on brass, etc. Or generating higher energy elements like chlorine, sodium. So let's take a look at a couple of examples of electrolytic cells here. When we're using electrolysis to generate high energy, potential energy species, then it can be in one beaker like this. So we'll throw in platinum. Platinum has a very low oxidation potential, so it means it's very hard to oxidize platinum. And then we'll hook up a power supply here, or battery, some external power. And then I'm going to use convention here. I'm going to hook the cathode of the power supply to the right electrode and the anode of the power supply to the left electrode. The cathode is positive, the anode is negative. Cathode is where reduction occurs, but that's for the power supply. For the cell itself, this would be the anode. The cell, which is going to generate electrons. And it's going to be negative here. So oxidation occurs here. So what is oxidized? Well, sodium. Is sodium oxidized? If sodium is oxidized, it would form Na2 plus an electron. Do you think it's easy to oxidize sodium? No. Because sodium has no valence electrons, only has core electrons. So if you were to oxidize sodium ion, you'd have to remove a core electron. It's not favorable. So this should be very, very low oxidation potential. Can we oxidize platinum? The oxidation potential for platinum is not in any of our charts, unfortunately. So if I go back to redox chart here and look for platinum, there's no platinum, but there's gold here. So platinum and gold are kind of comparable in terms of reactivity. They're both quite unreactive, very stable metals. And so if I see that gold is, the oxidation potential would be the reverse, so it would be negative 1.5 volts. It's pretty low. So I would estimate this, the oxidation potential for this is around maybe negative 1.5 volts, similar to gold. So this is just a guess here, around negative 1.5 volts, because it should be like gold. I don't know which one. Do you know which one's harder to oxidize, gold or platinum? Which one's more stable? So let's take a look at the. Actually, what we have to do is, now tables aren't oxidation potentials. Tables are reduction potentials. So if I'm interested in platinum, I have to look up the reduction potential of platinum 2 plus. No, it's here actually. Okay. So the reduction potential for platinum 2 plus is plus 1.18 volts. So if I reverse this, I get the oxidation potential for platinum metal, which would be negative 1.18 volts. And so negative 1.18 volts from internet. So which one has a higher oxidation potential? Which one has a lower oxidation potential? In other words, which one's easier to oxidize? Platinum or gold? It would be platinum, yeah. Platinum's higher. More positive, I should say. This is higher, more positive is going to be easier. So gold is more stable. Platinum is less stable. But if I didn't look it up like this in the table, I would just take a rough guess. It's pretty good book. Freeman really had it. Okay. Unfortunately, it's not in our book here. The platinum is a very common metal, so it would be good if it were in our book. Okay, what else do we have here? What else we have is sodium, platinum, and chloride. And that's it. This is molten sodium chloride, so we have to heat that up and melt it. What is the oxidation potential of chloride? Okay, well, that's in our book here. So we take a look. It would be here. So if we look at the reduction potential for chlorine here, it forms chloride. That's plus 1.36 volts. So the oxidation potential for chloride would be the reverse of this. It would be negative 1.36 volts. And so the oxidation potential for 2 chlorides going to chlorine plus 2 electrons will be negative 1.36 volts. Yeah, chlorine could potentially, well, we're looking at the reduction potential. So it's 1.36. It still shouldn't. It's still unfavorable, but a little bit of reaction can occur, even if it's unfavorable. So you shouldn't wear gold or platinum or copper in a chlorinated pool because although the concentration, it also depends on the concentration, but this is 1.36 volts, and gold is negative. Yeah, so it's getting close. And so it's still about negative 0.3 volts, but negative 0.3 volts is, and so it's not like all or nothing. So there's going to be some partial reaction. So yeah, you definitely don't want to do that. All right, so out of these, which one has the highest oxidation potential? It would be platinum. Now I know why they didn't put platinum on our chart. They didn't put platinum on our chart because the platinum is actually not going to react. What's going to react is the chloride. So this is an exception. You'd expect the highest oxidation potential to react. It just turns out that chloride is so easy to oxidize. There's one more exception that's very important. Chloride's so easy to oxidize kinetically, although you would expect this one to be pretty easy to oxidize as well. But it turns out that this one is oxidized here. So what we generate is, over here we generate chlorine gas. I have to check that reduction potential for PT2 plus. Let's see if there are other sources for that. This one they flipped the table upside down. All right. Okay, likewise, we go to this other electrode. So this is an exception. Fluoride kinetically easier to oxidize. Over here, we're forcing electrons in. So electrons are being forced out here. And we should oxidize the species with the highest oxidation potential, should be platinum, but we end up oxidizing this chloride, it's easier. Over here, we're going to reduce the species with the highest reduction potential. So what is the reduction potential for sodium ions? So we'll just go back to our chart from the book. The reduction potential for sodium ion is negative 2.713 volts. So sodium plus an electron goes to sodium, negative 2.713 volts. Then we have platinum. The reduction potential for platinum is very low, because we form platinum anion, Pt minus, and so we'll just say very low. Pt minus is a very, very rare species. Chloride also is very low because the extra electron has to be accommodated in the next shell. And so this would be Cl2 minus. This would be very low as well. And so over here at this electrode, we'll reduce the species with the highest reduction potential, which would be sodium. So over here, we're going to make molten sodium. Since this is molten sodium chloride, it would be melted. Sodium is less dense, so it will float to the surface. We need some kind of barrier here to protect it. And so we're going to form sodium liquid here in this case. Sodium liquid. This is under standard, and these are at 25 degrees C, so that would be a solid. So those numbers don't exactly match with the conditions that we have. This is molten sodium chloride, but what if we did it with aqueous sodium chloride? Let's say I didn't want to melt it. I just want to electrolyze. So let's build this cell again. Yeah. Rather than using platinum has a good electrical conductivity. We're going to use graphite this time. What we don't want to happen is we don't want the electrodes to react. And then in this case, I'm going to put aqueous sodium chloride in here. So I'll have sodium ions, chloride ions, and water. But then I'm going to force the electrons to go backwards by putting some kind of power supply here. Power supply, I'll put the positive terminal here and then force electrons into it. And so what I'm going to do is I'm going to oxidize the species with the highest oxidation potential. So let's take a look at the oxidation potentials here. Compare it to that. And so sodium ion, the oxidation potential is going to be very low. Or what is the oxidation potential? Is it plus 2.713 volts? Is that the oxidation potential? If this is the reduction potential, this is the reduction potential for sodium ion from sodium metal. Is the oxidation potential for sodium ion plus 2.7? It turns out it's not. That's the oxidation potential for sodium metal. Sodium metal is plus 2.7 volts. This is very high oxidation potential because sodium metal is so easy to oxidize. What about sodium ion? Is sodium ion easy to oxidize? If we oxidize sodium ion, what do we form? If we oxidize sodium ion, we form sodium 2 plus an electron. Have you heard of the sodium 2 plus cation? You haven't heard of it because In order to get sodium 2 plus, we have to ionize a core electron. So sodium loses its one valence electron and forms sodium plus. In order to form sodium 2 plus, you have to break into the core, and core electrons cost 10 times the amount of energy to oxidize over valence electrons. So sodium ion doesn't have a very high oxidation potential like sodium metal. Sodium metal plus 2.7, that's very high. This is very low, off the charts low. It just doesn't happen. Okay, what else can we oxidize? Well, we can oxidize chloride. If we oxidize chloride, well, chloride's stable. It's going to have fairly low oxidation potential. And we can see it's going to have fairly low oxidation potential because the oxidation potential of chloride is the reverse of this, which would be negative 1.358 volts. So negative 1.358 volts here. And that's going from 2 chlorides, this will go to chlorine plus 2 electrons. And then we have water. We can oxidize water. What's the oxidation potential for water? So for water, we'll go with this one here. Oxidation is reverse, so oxidized water to form oxygen, 4A plus 4 electrons. That's minus 1.229 volts. So if we take 2 waters, this is going to form oxygen plus 4H plus 4 electrons. And the oxidation potential for this is minus 1.229 volts. So which one has the highest oxidation potential? It would be the water. So over here at this electrode, I should be generating oxygen gas. But in order to oxidize water to form oxygen gas, the activation energy is quite high. That is, you have to break bonds in water to strip the electrons off the oxygen. Whereas to oxidize chloride, you just pluck an electron from its outer shell. So the activation energy is a lot lower. Here, the activation, so there's a big hump here. There's a much smaller hump here that we have to go over. This one, there's a big hump, but it goes farther downhill on the other side. This one's a smaller hump, but it doesn't go as far downhill on the other side, so it isn't as stable. And so kinetics wins over because, the hump size is going to make all the difference in the world. And so this is another exception. This is pretty much the only exception, this and platinum, that you need to know. So we predict oxygen gas to form, but what's observed is oxygen gas doesn't form. You know what gas forms? Chlorine gas forms. So we end up with chlorine gas over here. And that goes against, the highest oxidation potential would be water. But chlorine has a lower oxidation potential, but it has a smaller hump. And so this is kinetics. Because of kinetics, the activation energy is smaller, so it's easier to do. And so when it comes to chloride, there are a couple of exceptions. Pretty much one that you really need to know is this one. And then graphite, we can oxidize graphite, but graphite, we would say, is very low oxidation potential, so it's really hard to oxidize. Okay, over here, what would we reduce? Over here, we're going to reduce as the species with the highest reduction potential. So what species has the highest reduction potential? So we have graphite plus an electron yields C minus. This is going to be very low. We have sodium ions plus an electron. We use sodium metal. And this one we can look at. Yeah. So negative 2.713. And then we can also reduce water. And water is actually at the bottom of the chart here. And that is a negative 0.828. And so what happens with water is we take 2 water plus 2 electrons. This is going to yield H2 gas plus 4 hydroxides. Double that. No, actually, I've got H2 plus 2 hydroxides. And the potential for this is negative 0.828 volts. So which one of these has the highest reduction potential? Water. So what's going to happen here is I'm going to reduce water. Hydrogen is going to take those electrons, and what we're going to end up with is H2 gas. So this is the cathode of the power supply. This is the anode of our electrolytic cell. At the anode, what gets oxidized? Chloride gets oxidized. Oxidation occurs at the anode. Over here, reduction occurs at the cathode. This is the cathode of our electrolytic cell, which is hooked up to the anode of our power supply. And what gets reduced? Hydrogen gets reduced. Now, our book is going to call, just because of convention, our book is going to call the whole thing the cathode, the whole thing the anode. And so when we look at this, we have a little footnote here. It says, note that the sign of each electrode in an electrolytic cell is the same as the sign of the battery. And what they're going to do is they're going to call the whole thing the cathode here. This whole thing is going to be labeled the cathode. But it's weird because oxidation doesn't occur at the cathode. And over here, they're going to label the whole thing over here the anode. And again, this is weird because reduction does not occur at the anode. Label that. So this is kind of an interesting cell here. Here they put in salt water, and they get chlorine out, as we expected. You know, when it comes to water versus chloride, water has a higher oxidation potential, but chloride gets oxidized because of kinetics. So chlorine is generated. And then that's what we're going to form at this side. At the other side, we expect to form hydrogen gas. But in this case, the sodium ions get reduced. The sodium ions get reduced because they end up stabilizing that using mercury, liquid mercury. And so they can extract it, sodium from there. And when it comes to reducing water, the activation barrier is kind of high because we've got to break bonds here. But when it comes to reducing sodium, it's pretty straightforward, even though there's a huge difference here. Changed. And so what they end up with is sodium and liquid mercury. And then that gets dumped into water, and the sodium can react with the water to form hydrogen gas. So eventually we get the hydrogen gas, but this is kind of a weird setup, and it's set up in a way that we can promote these reactions from occurring versus the reactions that we would have expected. We can do some stoichiometry with both types of cells. Galvanic voltaic cell, which is the battery, and the electrolytic cell. As long as we measure something, and that something is time in amps, time and current. So if we have time and current, then we can measure amounts of reaction. And so the current is the most important. That's amperage, or amps. Amperage is the flow of electrons here. And 1 amp is defined as the flow of 1 coulomb's worth of charge in a second. And then if we know the time, we know how many coulombs were transferred. If we know how many coulombs were transferred, then we can use the Faraday constant to figure out how many moles. And so once we know how many moles of electrons, then we can figure out how many moles of species we have. So there's something missing here in the stoichiometry, that is time. Then we can get that coulombs. And so let's do an example here. Let's say in this electrolytic cell that I just erased, we ran it, we operated it for 60 minutes. So if we operate the cell for 60 minutes at a current of 100 milliamps, how much chlorine, CO2, do I generate? Is generated, produced. So 60 minutes time, and then 100 milliamps would be 0.100 coulombs per second. So I would do this. I'd go 60 minutes, and then I want to convert that to seconds, so 60 seconds per minute. And then I'm going to use this, 0.100 coulombs of charge in a second, 800 milliamps. And then I'm going to use the Faraday constant. The Faraday constant is 1 mole of electrons contains 96,485 coulombs worth of charge. And then I'm going to use the half reaction here. The half reaction is 2 chlorides goes to chlorine plus 2 moles of electrons. So for every mole of chlorine, I have 2 moles of electrons. So 1 mole of chlorine is produced when 2 moles of electrons pass through. And then I know the molar mass of chlorine, which is 70.90 grams per mole chlorine. So I can go ahead and calculate the stoichiometry of this. That would be, and then it doesn't matter if it's a voltaic or electrolytic. It's the same calculation. 60 times 60 times 0.1 divided by 96,485 divided by 2 times 70.9. 0.13227 grams. 0.13227 grams of chlorine. In other words, 0.13 grams. So this would be the stoichiometry that we do here with this. Okay, I guess, are we out of time?
For the quantitative analysis report, did you want it like how the reports are, or did you actually no?
Qualitative analysis reports is going to be very simple. Just the cation list of positive and the anion list of ones to test. I don't need to know the negative ones. What's that? I said something about what? Well, yeah, the formal reports The formal reports you can turn in on the day of the final, or you can actually turn those in after the final if you need more time. If you turn it in after the final, you can turn it in on Friday or Monday at the latest to the office and just ask them to put it into my mailbox. That goes for any old reports and homework too. If you have that, you can turn that in to the office. Late papers will go there, but the due date, you won't get any late penalty if you turn in the form on Monday. But the problem is if you wait till after Monday, then you're not going to get a grade for it because the natural science office. They should be open on Monday because of summer session is coming out. I got to prepare for that. Monday evening, I'm going to come by and pick up all the papers. And so that's a hard deadline because I'm not going to come back on Tuesday. What's that? What was what? What was the formal report on again? It was on the titration and the synthesis. Yeah, and so those two are the formal reports. And those two you can turn in, without any penalty till Monday. A lot of people are already done with one or maybe two of those. Yeah. You'll have a little bit of extra time if you need it. No, we're going into the normal lab tomorrow. In the normal lab, my plan in the normal lab is you're going to have a brief survey of 24 and 25. Chapter 24 and 25 only made 10 slides for that. And then we're going to check out. Tomorrow we're going to build, I think we still have to build a model or two. Did we do the tetrahedral?
Yeah.
Oh, okay. Did you do the octahedral? The cis strands? Maybe, well, you probably don't have to build it. We'll see. Tomorrow, but we're going to check out a lab tomorrow. Okay, and then I'm going to cover this, and then we'll have a review starting tomorrow.
And then no more new material.
Yeah, no more new material, and this is going to be just a brief survey. It's not really going to be a full.
And for the final, is it going to be detailed?
No, multiple choice, and so the types of questions aren't going to be like these advanced, integrative, advanced type problems where you have so many steps. It'll be simpler. Right, kind of, except maybe some more calculations. But they'll be pretty much the basic.
Okay, more basic.
Yeah.
Concept.